Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is ADM 2020 Member Design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your moderator, answering any questions you may have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance I don't get to all your questions, we will certainly send you a follow-up email afterwards. So I want to quickly go over the content for the next hour today, and we'll be working in a series of standalone programs as well as add-on modules. So to begin, we're going to create a custom extruded section in our standalone program Shape Thin. So this will allow us to import in a DXF file to calculate the cross-sectional properties. Then we're going to integrate this section into our FEA program RFEM, where we'll begin modeling our aluminum member structure. From here, I'm also going to utilize some fabric membranes for the aluminum structure, and we'll utilize the add-on module RF form finding, which will allow us to calculate the form finding shape of these fabric membranes and cable elements. We're also going to use our standalone program, RWIND Simulation. So this runs a computational fluid dynamic analysis to essentially integrate this structure into a numerical wind tunnel. We'll calculate the wind loads, we'll integrate those back into RFEM for the static analysis. And finally, we're ready to run the full analysis in RFEM for the consideration of all load cases and combinations. From this information, we're going to get all of our member internal forces, our deflections, our support reactions. And then finally, we're going to utilize the add-on module RF-ALUMINUM ADM within RFEM to do aluminum member design according to the latest ADM 2020 standard. So I know that was quite a bit of information, but I believe as we work through this example today, it'll make a little bit more sense how all of these programs and add-on modules will work together. So let us begin in our standalone program Shape Thin. And where I'll begin is to import in under File, Import, a DXF file. So this comes from AutoCAD, and as you can see when I click the Open button for this DXF file, I have the ability here to activate this C over T parts. And you'll hear me say this quite often today, but this is the powerful thing about Shape Thin, that we can calculate these width to thickness ratios, so these C over T elements. And with that, we integrate this back into RFEM that allows us to also check local buckling of these custom extruded aluminum sections. I know there are some other programs out there that will, of course, calculate the cross-section properties, but something that may be a little bit more unique and powerful with Shape Thin is the ability to also, again, check local buckling with these C to T elements. So I can click OK through these dialog boxes, and now we'll be presented here with our drawing grid where I can just simply click here within the origin to get a background layer of this cross section. Now, it's not quite as easy as just clicking a button and calculating the cross-section properties. What we need to do is to create these elements that make up this section. And again, the reason why we have to do that is because this will allow us to calculate those width to thickness ratios as well that the program wouldn't be able to automate otherwise. But we have some helpful tips and tricks within this program that will allow us to do so. Under Edit, we have the ability here to set elements with the DXF template. And the first option is to set the center lines. So what this will allow me to do is to click two of these lines, and automatically the program will create the center line between these two DXF background lines. And I'm only going to do a quarter of this section because everything is symmetric. So once I get a quarter completed, I can use the mirror tool to kind of create the rest of the cross section here. So once we've set these center lines, the next step would be to set the elements. And I do need to define a material here. And quite honestly, the material really doesn't matter within shape thin, because what we're going to end up doing is redefining this material once we get into RFEM. But shape thin does require something to be set here in order to calculate the cross-section properties. So you can see that under the ADM standard, we have all of our aluminum materials. Now I added a particular material to my favorites group here that I can just quickly select aluminum 6061. Again, this is really irrelevant because we're going to end up redefining that once we're in RFEM. Then I can simply click on these center lines. You'll notice that the elements are automatically set. Now we do need to clean this up just slightly, and we can do so by dragging and dropping to the relevant points here. And once we do this, which we can zoom in here, with both of these elements on the left, you'll notice that this is the width to thickness element shown here. And the program recognizes what's closed on one side and what's open on the other, which is important for local buckling considerations within the aluminum design manual. So now that we have these elements set here in the upper left, what we can do is to highlight them, and I will unselect my C to T ratio over on the left. I'll use my mirror tool. And a mirror tool is something that we'd see similar in AutoCAD, where we can create a copy, we can mirror about the Y plane, and then I can graphically choose my mirroring point here. I click OK, and now I can see my elements generated at the bottom. And finally, we have the same process that we need to do on the left-hand side, where I'll deselect these elements, these C to T ratios, top and bottom. We use our mirror tool. This time we mirror about the Z-axis. We choose our mirroring point somewhere in the center here. I click OK, and now our element is complete. Now, one thing we need to do, we can only check local buckling of these straight elements. So currently we have these C to T ratios set for the curved elements as well. And if we kept those and we went into RFEM, we'd actually get an error message just saying, hey, we can't check local buckling of these small curved elements. So what I'll do is just delete those altogether on my keyboard, but we still have them for the straight elements here. And we're finally ready to run our calculation. So all I need to do is to click Show Results. The program begins the calculation, and I'm immediately presented with an error. It's telling me that FY for my material is not positive. So what does this mean? Well, if we look at the table for this particular material that I've set, you'll notice that the yield strength and ultimate strength are set to 0. And the reason why for aluminum, we have different strength values depending on if the member is in tension, compression, and shear. So again, we just need to set some arbitrary value here in order to calculate these cross-section properties. So I can just set 35 and 42. It really doesn't matter. I try and run this result again. The program does give me one more warning message just saying the load case was not defined. That's fine. We're not doing a stress analysis within shape thin. We're just calculating these cross-section properties. And now you can see that after the solution is run in our table, here is all of the cross-sectional properties for this custom extruded section, including the area, the moment of inertia. We have here the section modulus, so everything that we'll need to integrate into RFEM. Now, it's really important that we save the calculated results here. If we do not save, once we bring this into RFEM, the program won't know the cross-sectional values. So be sure to save that, and we are now ready to jump into RFEM. So here is our main FEA program, and you can see the interface looks pretty similar to what we just saw within shape thin, but this is where we'll be able to generate our entire structure here. So I have my graphical interface, and I'm going to begin by modifying my drawing grid here, and I'll start off by drawing a few nodes. And I'm going to go up here to my toolbar, and I'll choose New Node, and I can either select it graphically here on my drawing grid, or I can just type in the node coordinates directly. So we'll start off with 0, 0, 20. I hit Enter on my keyboard, and that first node is generated. The second node will be 0, -10, and 17.25. And finally, my third node is going to be 0, -30, and 0. So I have these three nodes that are generated that will somewhat form the left side of my arc here. I'm going to draw a new line element, and instead of a straight line, we'll choose this option, an arc. I click on my second point, I click on my third point, and then you can see I can either select the radius graphically or I can type in a radius of 30 feet. I hit enter, and I'm going to take this arc, right click, divide the line by a certain number of nodes, and I will set this to 3 intermediate nodes. And the entire purpose of this is I'm going to take some of these node elements here and completely delete them. So all that I'm left with is just a series of nodes that are again going to form the left side of what will be my arc frame here. So I'm going to draw a new member now. And the new member will be the member type set to beam. And I want to generate a new cross section. So I visit my cross section library. And of course, we have all of the cross sections from the ADM standard, which we'll get into in just a minute. But for this first member, I want to integrate that custom extruded section from Shape Thin. So I can choose that with this button down here in the lower right-hand corner. And immediately I navigate to where my saved results are, and we see that custom extruded section. Now, just for your reference, if we tried to access one of the other shapes and we didn't save the results, we would see some type of error message such as this, just saying that, hey, you need to calculate and save the results. But for us, we went ahead and did that. So I click OK. Then we also need to set the material. Now, my material is already set, but likely if you're creating this section for the first time, what you would see here is maybe a steel or a concrete material. So we can always access our material database. And this looks familiar. We've already seen this in Shape Thin, where we can use our filters over on the left to navigate to aluminum, to the ASTM, and to the ADM 2020. And again, we have just about every aluminum material that you would need here. We can also take advantage of our search functions here to select the relevant material. All the material properties are given to us within this table format. So once we have the material set, I can click OK through all of these dialog boxes, and I can begin modeling my first series of members. And I'm just really snapping from one node point to the other here, and we'll finish at the top of the structure. Now, notice something also powerful about integrating from Shape Thin is that we actually get the rendered shape here. So I know with sometimes general sections, we're just kind of getting some type of blob outline here, but we'll actually be able to tell the orientation of that cross section based on the rendered shape. Now, we'll also notice that these are a series of individual segments, and in reality, we'd like to design these as one continuous member. So what we can do is to highlight all of them, right-click, and under Member, we have the ability here to create sets of members. And this isn't going to modify the analysis. All this will do will to group these series together. And once we get in the RF-ALUMINUM ADM module, we can actually design this as one continuous member. So we'll see this set of member symbols. If we zoom in here, it's just a faint dotted line kind of grouping these all together. So we have the left side here. I'm going to highlight all of my elements, and I'm going to utilize my mirror tool. I'll create a copy. I'm going to mirror about the XZ plane, and I can mirror about the origin 0, 0, 0. I click OK, and now we have the right side to our arch here. Sets of members was also copied, so I don't need to worry about grouping those all together. Okay, so I'm going to take all of these elements with my selection window here, and notice that I'm selecting all of my elements except for my bottom two nodes, and there's a reason for this. I'm going to go up here to my Move Copy tool, and I'm going to create 4 copies in the global X direction of -16.5 feet. And I'm going to visit this detail settings here. Within the detail settings, I have the ability to create copied lines between my copied nodes. And even more so, I can assign a particular cross section to them. So I create a new member, and this dialog box should look familiar. We're going to create now what's called a truss member. So a truss will just internally apply a moment end release to the beam. And you can see under here, under the member hinge options, this is automatically grayed out because the program will apply this by default. And we do need to create a new cross section. So I go to my cross section library, and this time I'm going to choose a tube section. And within the tube section, you'll notice here that if we use our filter once again to filter to the ADM 2020, we have all of the relevant cross sections to this particular standard. And we scroll down here to choose a 6x6 by 0.375. Now I've already defined that aluminum material for my first beam, so I don't need to define it again. I just simply select it here from my drop-down box and I click OK. So I click OK through all of these dialog boxes, and now we'll notice that the program has generated these truss elements in between my copied nodes. And under the display tab, if we scroll all the way to the bottom, we can view these members by member type, and now we can see which ones are defined as beams and which ones are defined as truss elements. Now, something to notice about these tube members spanning in between our main frames here, if I turn this to wireframe view and I scroll up here to my display options and I view the cross-section outline. Well, the tube elements are oriented here according to my global X, Y, and Z axes. You know, they're just kind of facing in the vertical direction here. But in reality, I'd like to see them somewhat angled to kind of follow this arc radius along the main frame here. So how do we adjust each one of these without having to manually do it? Well, under the Views tab, I am going to select the option here to view the members by type, and I'll select all of my truss elements. So now everything else is grayed out within this model. And before I select all of these truss elements, I'm going to create a node. And we previously saw how to create a node, so this should be familiar as well. The node coordinates will be 0, 0, negative 11.77, and I click OK. So now you'll notice I have this node right down here, kind of at the center of what would realistically be this circle here. So this defines maybe the radius point, the origin point to the radius here. I select all of my truss elements. I double click them to edit, and we have the ability here to rotate each one of these elements based on a help node. And I can graphically select this help node, number 56. I click OK, and now when I zoom in, you'll notice that each one of these are angled and they're pointed directly toward that help node at the bottom. So that's just an efficient way in order to manually apply that angle of rotation to all members at once rather than having to individually select them. Okay, so we will turn off the cross-section outlines. Let's cancel our visibility here. And the next thing to do is to address our lateral bracing. And for this, I am going to draw a new member. The member type here is going to be the type tension only. And tension only is exactly as it sounds. It can only take tension forces. The minute it experiences any compression, it's taken out of the calculation. It can be reactivated though. So if we do see tension again in the next iteration, it will be reactivated. Member hinges, everything's grayed out here. Again, because that element is only going to take those tension forces, no moment, no shear, no anything else. So we visit our cross-section library, and for this, I'm going to choose my round bar. And we're going to assume this is some type of cable type element with a diameter of 0.5 inches. Now we do need to define a new material. You can see that in my model, I already have it defined, but once again, we visit our cross-section library. We do have a few manufacturers here if we visit the filters under cable. So perhaps you find your manufacturer here, but most likely you're going to have to create a new material with this button down here to specify the specific material properties for your particular manufacturer that you're using. Now you can see I've generated just a general ASTM cable material for myself for example purposes with the relevant properties. I click OK. And then it's really just as easy as snapping to these points from node to node within this first bay to create my lateral bracing. And I'm only going to do the left side here because once again, we have a symmetric section, so we can utilize that mirror tool. So I'll rotate this structure around. I'm holding down my control key to select all of my X braces. We're going to use the mirror tool. We're creating a copy about the XZ plane. We're going to mirror about the origin. The one thing I need to do here is to uncheck the option to create lines between my copied nodes. I click OK, and now we can see the X bracing on the adjacent side. All right, so we have all of these elements defined. The final thing to do for our supporting aluminum structure here is to go ahead and draw some columns and beams at the front and rear of the structure for additional support. So I'm going to turn on my grid element and we're going to draw a new member. This time the member type will just be a beam. We are going to select our 6x6 that we've already defined with the relevant material. I do want to define a member hinge here. So at the member end, I'm going to create a new member hinge definition. Now the program automatically assumes we want to release the moment about the local Y and local Z axes of the member, and this would be the definition of a moment end release. So we can go ahead and click OK, and now we can see that definition defined here. I click OK, and then it's really as easy as snapping from this origin up to my frame. So I'll do that at 3 locations here. I right click a couple times and I'm going to repeat the new single member. Same exact concept for my small little beam elements, but I am going to apply a member moment release here at both the start and the end. I click OK, and then I'm going to snap to the midpoint of the column on my left. The program detects what is the perpendicular point with my snap settings, and now we have a couple beam elements drawn in here. Now, similar to my main frame elements that we saw before, I'm going to take each one of these series of members that were broken apart because of the beam. I right click and I'm going to create a set of members here for these 3 elements. I click OK. So now we have sets of members defined for those columns. I take all of these elements, I highlight them, I can hold down my control key, and I can actually just drag and drop to make a copy to the rear side. So in all reality, our structure is complete for the aluminum modeling. The final thing to do here is to apply a nodal support at each one of these points down at the bottom. So I can draw a new nodal support, and we'll just use the default option here, which is typical pinned application. I click OK, I can rotate my structure around, and this way I can select all nodes at the bottom. And now you can see I have that pin nodal support applied to each one of these members. So we are going to take the next step and apply the fabric membranes to the rest of the structure utilizing the RF form finding add-on module. Now, because this is an aluminum webinar and I want to focus a little bit more on aluminum, I will jump to an already saved model here where you can see these fabric membranes have already been modeled. So if we're taking a look at one of these, I'll just give a brief explanation here. If I take a look at the surface, the stiffness is set to membrane orthotropic. And I did define a material here. So if we take a look at the material settings, the material model is set to orthotropic elastic 2D. And if we look at the detail settings here, it's exactly as it sounds. With orthotropic, we have different stiffness properties in both the X and the Y direction. So this might be information that we get directly from the manufacturer for modulus of elasticity, shear modulus, and so on. So once I've set the material here, we can go into the detail settings of these orthotropic membranes. And under constant thickness, we've set the thickness to 0.03 inches. And we can view the stiffness matrix. Now notice we only have entries for the D66 through D88 for this surface, and that's because it was defined as a membrane, and it will only take tension forces, in-plane tension forces. So that's why we have maybe a smaller stiffness matrix than what we'd see with a typical standard surface. Now finally, this last tab is only available when we've activated this RF form finding module. So what this allows us to do is to set a pre-stress force, for example, and I've set this at 0.07 kip per feet in both the X and the Y direction. The program will automatically calculate the relevant form finding shape for me based on these pre-stress forces. So I click OK through all of these dialog boxes. That's just a brief overview. And I also have cable elements defined at the bottom here. And these cable elements define the boundaries here for my fabric membranes as well. Now the member type is set to cable. So this is a little bit different than our tension only members. And the reason why, if I go into these detail settings, again, utilizing the RF form finding add-on module, I have the ability to set a pre-stress force of 2 kips. And I can model this cable element completely straight. And the program, in particular the form finding module, will find the catenary shape for me based on these preliminary settings. So pretty powerful in the sense that we don't need to determine what the catenary shape is and model this manually. The program will do everything for us. The final thing I just want to visit in regards to the form finding, if we turn this into wireframe view, you'll notice that we have quite a few more nodes visually shown to us here, and there is a reason for that. So I'm creating a visibility by the selected objects here. And remember, we created those truss elements. Well, what I've done here is I've actually dropped this truss element about 6 inches or so below my fabric membrane. And then I have these rigid links connecting the truss element back up to the fabric membrane surface. And these are spaced at about every 1 foot, which is the length of my FE mesh. Now, what's so special about these rigid links, if I double click on them, they have a member hinge set here. If I look at the detail settings, I've actually released the translation at the top of these rigid links to allow the fabric to slide over those tube elements. So I have no restriction. They can just simply slide in those translation directions here. What else I've defined for these rigid links is a member nonlinearity, so that this member fails under tension. What this means is when the fabric has uplift, we're not going to see any connection between the truss element or this tube element and the fabric membrane. That bond will essentially be broken. But if we have downward deflection of the membrane, that tube element will catch the fabric. And this will make a little bit more sense as we view the deflected shape under the various applied loads. So I just wanted to briefly explain, what all of these various nodes are shown at these truss elements. So that was just to kind of tie in together the fabric membranes with the tube elements and giving us the ability here to apply these nonlinearities to take into consideration the true behavior. Okay, so if we cancel out of this visibility here, what we can do is to begin by running the form finding module. So that's the only so-called load case I have defined here, and that automatically pops up. And again, we are just taking those pre-stress forces from the fabric membrane and the cable elements to determine what the relevant shape is. And we still have this aluminum structure underneath the fabric membrane supporting the rest of those elements. So we can see the progress bar down here on the lower left as well. The program's just running through those iterations to find the relevant shape. So once we are done running the form finding process, we can see the relevant shape here. So our cables now have some type of catenary shape here. Our fabric membranes look accordingly based on that 0.0 kip per foot pre-stress value. So the next thing to do then is to move forward with the rest of our load cases. So I'm going to generate a new load case here. And the first load case will be set to dead load, and I'm going to activate self-weight here. The second load case is going to be a general snow load with the action category set to snow. Now, I will create a couple wind cases too, but I'm going to utilize RFWIND Simulation, or our RWIND Simulation, which is the standalone program, which will automatically create those load cases for us. So nothing to worry about now. We're just going to focus on these 2 load cases. So for our dead load case, we select it here within our drop-down box. And let's just say we want to account for maybe some additional dead load along these main frame elements. And we can do so with a new member load. And I'm going to apply this to the sets of members. And the sets of members just might be a little bit more efficient than manually applying to each individual member segment. We'll apply it in the global Z direction. The magnitude will be negative 0.08 kip per feet. I click OK, and let's go ahead and let's see. I guess I need to set my members first. Let me try that over again. So if we go up here to draw a new member load, there we go. I must have selected the wrong application. We'll choose sets of members in the global Z direction, negative 0.08. So you can either set the members previously if you have them selected graphically, or in this scenario, we will just select them after we've input in the load magnitude. So as you can see, I can click on my sets of members on the left-hand side. We also could use the mirror tool once again, but it's really just as easy to also click these sets of members on the right-hand side as well. So you'll notice that once we are done applying this member load to those sets of members, everything's shown graphically to us here. So moving on to the snow load. So we want to make sure the snow load is available to us within this dropdown, and this will be a surface application. So I choose a new surface load here. And the load direction is going to be in the projected Z direction. So what does projected mean? Well, at these locations where we have a little bit more of a steeper angle, we're obviously not going to see as high of a snow load at these locations as we would where maybe our membranes start to flatten out at the top. So the projected load will take that into consideration. We give it a magnitude here of negative 0.005 kips per square foot, something relatively small, and then we can highlight over all of our surfaces here graphically, and now we can see that projected load applied to the top of our structure. So we're now ready to move on to wind loads. And for this, of course, we can manually apply our wind loads, but I want to take advantage of our standalone program, RWIND Simulation. Under Calculate, we can see here RWIND Simulation, and this is just the integration dialog box between the two programs. And I will say that I'm going to go over this rather quickly just for the sake of time, but I have done previous webinars that go much more into detail on RWIND, including all of the details for the input data. I go through the results in much more detail than what we'll have time for today, so certainly refer to our YouTube channel for that. But just to give you a brief overview, what we can do is to define the wind load directions we're interested in. So for example, we can choose 0 degrees and 90 degrees. And what this means is we'll have a wind load from the X direction as well as the Y direction. And under the wind profile, this just defines the wind speed that will be entering in this numerical wind tunnel for our structure. We do have a few standards integrated within this drop-down box. So you can see here the ASCE 7 is available, the NBC, the Euro code. So sticking with the ASCE 7, we would define some information specific to the standard, such as the exposure category. We could leave this as B. Maybe the wind speed is somewhere around 105 miles per hour for the basic wind speed. And then the rest of the factors, we'll just leave this as 0. Now you also have the ability to choose a user-defined option here where you can fill out the table of the wind velocity as a function of height. Under the second tab, these are our two load cases that will be generated. So notice load case 3 and load case 4, which will follow after load case 1 and 2 that I've already defined. Under the settings tab, we have some various default settings for most of this input here that we'll just go ahead and go with today for example purposes. But the one thing I do want to point out that we've recently added is this option here to keep the RWIND simulation results if the mesh is deleted. So what this means is if you're just making minor changes to your RFEM model, we have the ability now to keep the pressures, the wind pressures from RWIND simulation, where previously if we deleted the mesh in RFEM, our RWIND wind loads were also deleted. So this will be definitely a significant time savings if you're just making those minor changes. So back under the load cases, what we have the ability here to do is to calculate all in the background, or we can open up any one of these load cases in particular in RWIND simulation. So once again, for the sake of time, I have a model here where I have already calculated these wind load cases. So for example, we can take a look at wind 90 degrees and we can open an RWIND simulation. So what this will do is to launch the standalone program. And what we'll be presented with is initially the results of our structure, just because I've already run that calculation. But this is what is brought in from RFEM. Here is my exact structure, including the fabric membranes, all of my lateral bracing, those tube elements, those custom defined sections. Everything is imported into this numerical wind tunnel that we can see here. And the wind flow is going to be from left to right through this tunnel. So once we calculate the results, what we're presented here are the wind pressures on the structure. So I can actually hover my mouse over the different locations, and as expected, we see the highest wind pressures here where we have the wind entering from left to right. But as we move around the structure, we're going to see decreased pressures, and towards the back, we're going to see, of course, some suction. And we also have different forces on the interior of the structure as well. So both can be accounted for within this wind tunnel. We even have some pressures here on our individual members. Now, a few other ways to view our results, we can view the flow field quantity. So what this is just the wind pressure around the structure, and we can grab this graphical view here and kind of slide that back and forth if we're interested not on the structure, but around the structure. Same concept for the velocity vectors here. So this is going to be the wind speed that is around our structure. We can see the color-coded format here in feet per second of how exactly that wind flow is moving around. And finally, everyone's favorite, which are the streamlines. Streamlines are just going to show how those particles are moving up and over the structure. We can see we kind of have a swirl effect on the interior of the structure, which is often hard to capture by just general standards. Of course, those standards may give us some minimum design loads, but it might be interesting for us to take these unique structures in here to kind of see the movement of the wind itself. So we also can activate the streamlines animation. So we can see the exact movement of these particles up and over the structure and again in the interior. So quite a few different ways to view our results as far as those wind pressures in and around the structure. The member forces is also available to us. This might be interesting because this will allow us to graphically see which members are experiencing the highest forces from this wind load. But ultimately, we're referring back to the pressures here, and these pressures are what is going to be integrated back into RFEM. So what I can do is to exit out of RWIND simulation. And what we'll see are a couple more load cases here. Load case 3, wind 0 degrees, and we actually can turn on the view of these loads. Now this is completely overwhelming, but if we zoom in, what we see is happening here is that the program has taken those wind pressures from RWIND simulation, it's converted them into forces, X, Y, and Z forces at every single FE mesh point for this structure. So you can imagine how incredibly powerful this is for very unique shaped structures and the ability to calculate these wind loads for really any type. So once we have these 4 wind load cases, or sorry, these 4 load cases in general, dead, snow, and wind load defined, you can see the program automatically generated all of my load combinations according to the ASCE7. So we're finally ready to run our analysis on the structure. Well, again, I've taken the liberty here just to run the calculation for the sake of time. So once we run this calculation, we are initially presented under our results tab in our project navigator with the deformations. So we can view for each one of these load cases or load combinations, just the behavior of the structure under the applied load. So dead load may look as the following, in addition to dead plus snow. And you can see in this downward deflection, as I talked about, and we'll see this with the following load cases as well, that when we have pressure here on our fabric membranes, these truss elements we can see on the other side are going to catch it. So we have that full integrated behavior between those truss elements and the fabric membrane. In comparison, when we scroll to some of these other load cases where we begin to have uplift here, that's where we're going to see the fabric membrane lift away from those truss elements. So the true behavior between those two elements can be considered with those nonlinear rigid links. So the deflection is important because I believe that this gives us an idea if we've modeled everything correctly, we don't see anything flying off the page. But for aluminum design, we're most likely interested, of course, in our member internal forces. So here we can activate the internal forces graphically. And what I'm going to do under my Views tab is I'm going to select only my sets of members. So now you can see that everything was grayed out in the background. So I just have those sets of members activated. Well, back under the results tab, this allows me to view the axial forces or normal forces along these sets of members, for example. We can view shear forces in both the weak and the strong axis direction. We might be interested in our moments, which we can see we have some positive bending moments on the exterior. When we look up at the top, we have some negative bending moment. Now, for any one of these members or sets of members, we can always right-click on the element to visit what's called the results diagram. And the results diagram allows me just to view in a bit more detail what's occurring with the internal forces along this full member length. Now we even can change the load combinations up here at the top. We can export this information to Microsoft Excel. We could add these graphics to our printout report. So quite a bit of information that is available to us just in a bit more detail than what we can see graphically. Now, of course, we can also view the stresses here, the strains for our members, and everything is given to us not only in this graphical view within the Project Navigator, but we can take a look at our member internal forces within table format. So what's nice is that as I'm clicking through this table, you'll notice that everything is synced up in the background. So I have this big red arrow pointing me exactly to where this controlling internal force is, whether it's the axial force, the shear force, bending moment, and so on. This we can also export to Microsoft Excel. And this might be important if we're taking it upon ourselves to do the aluminum member design either manually, maybe with Excel spreadsheets, or perhaps we have some in-house tools. So you can utilize RFEM for the analysis portion only. But of course, in just a minute, we're going to be utilizing the ADM module to get more into aluminum design directly within the program. So in addition to our member internal forces, we have some information on our surfaces as well, but I'm not going to explore that in too much detail today with our fabric membranes. Again, previous webinars that go much more into detail about fabric membrane design within RFEM utilizing the form finding add-on module. We can view our support reactions here. We can see all of this shown to us graphically, and of course in table format, we can see the support forces as well with everything synced up here with our red arrow. So that really gives a complete summary of the analysis portion. And now we want to make the clear distinction that we'd like to jump into the aluminum design module to perform the aluminum design portion of our example today. Okay, so how we can do this is under the data tab, you can see our long list of add-on modules here. You can see RF-ALUMINUM ADM. I have added this as one of my favorites, so it jumps it up to the top of the list. We also can access our add-on modules here, which they're categorized in a little bit more of a format based on the material types, such as design for aluminum. We'll see here RF-ALUMINUM ADM. Now, this add-on module is just going to be a dialog box that pops up within the main program. And sorry about that, jump to shape thin. So just a simple dialog box here. Now, we don't need to remodel any of this information. A majority of all of our information is going to be brought into this add-on module. The purpose is just to define some information that is more specific for the design process. So you can see here over on the right-hand side, we have our drop down to select the various standards. And we have the 2020, which we recently added, both ASD and LRFD, but we still have access here to the 2015 and 2010. For today, we'll be moving forward with the LRFD 2020. Now, before I get into more detail here with the example, I want to jump back to the PowerPoint just to explain some of the updates that have taken place with the 2020 standard. Now, by no means is this a complete list of all of the updates within the 2020. It really is only the relevant changes specific to RFEM and RF-ALUMINUM ADM that I wanted to cover. So what has been updated within our program? The first relates to Chapter B design requirements. So previously in the ADM 2015 section B22, we had the bridge type structures that were addressed. Well, we'll find within the 2020 that this section was actually removed entirely. So a little bit of history about this is that back in 1967 or around this time period, we started seeing aluminum bridges kind of pop up all over the US. So obviously there needed to be some type of design standard that addressed this. So the ADM took it upon themselves to go ahead and add bridge design into their design standard according to ASD design method. This did require that bridges and buildings have different safety factors. So it wasn't until 1994 that AASHTO published the first LRFD specification, and they actually did include aluminum bridge design for LRFD. So as a result of this, ASD kind of lingered on within the ADM, even though ASD design is no longer permitted for aluminum bridges. So that's why within the 2020, that was completely removed. So within the detail settings of the RF-ALUMINUM ADM module, if you are running the 2015 or 2010 ASD design, you will still see this option here to define whether it's a building type structure or bridge type structure. If you choose the ASD design for 2020, this option is now gone. So moving on to Chapter F for flexural strength, we have here the direct strength method from section F32, and this all relates to local buckling. So previously in the 2015 ADM, this section F32 referred directly back to section B555. So you can see over on the right-hand side, just a quick screenshot with that reference made here. So this required all elements within our cross-section to be classified under uniform compression or flexural compression. And the reason why is because B555 only addresses elements in flexural compression. So we kind of had to determine, which elements fell under which category back in Chapter B. Well, now with the 2020, you'll notice that all of these equations are listed directly within this section, F32. And although it looks more complicated, this is actually a huge simplification because we no longer have to go through each element and classify it as uniform compression or flexural compression, but rather the nominal flexural strength equations are given directly to us that we can apply to all elements. So simplification is shown here for that 2020. Also in Chapter F for flexural strength, we'll see some differences with the bending coefficient C sub B equation in section F41. So looking at the 2015 equation, we can see this shown on the right-hand side. Now, when we compare that to the 2020, right below it, we can see obviously some differences here. Now, this equation from the 2020 comes from the Guide to Stability Design Criteria for Metal Structures and the 6th edition. So again, this is another simplification here where previously in the 2015 ADM, we had two separate sections with the C sub B factor, one for doubly symmetric shapes and one for singly symmetric shapes. Well, now for the 2020, we've combined both of those sections. We have one single formula here, and to account for that, we have introduced the R sub M variable, and the R sub M variable shown here within this equation will address singly symmetric members. And finally, within Chapter F, flexural strength, we have single angles from section F5. So all of the updates within the ADM 2020 are consistent with the updates from the AISC 360 2016 manual. So I don't have a complete screenshot here of the list of all of the changes that were made. So you'll definitely want to refer to the code, but just to name a few, for example, we're seeing a lot of changes here with the lateral torsional buckling strength M-sub-E from both section F5.1 as well as section F5.2. F5.1 is going to be bending about the geometric axes, and F5.2 is going to be bending about the principal axes. So again, doing just a quick comparison here, when we look at equation F54 for the leg tip and compression, we can see the difference between the 2015 when we compare that to the 2020 with these coefficients here, just a different value. Same thing for the leg tip and tension, equation F5-5, again, different values here for those coefficients. We're also going to see further simplifications in section F5.2. So this is for bending about the principal axes, for major axis bending for equal and unequal leg angles. So again, refer to that section. You'll notice the differences between the 2015 and the 2020. Okay, so what we can do now is to jump back to the aluminum module and begin just the rest of our input here for our member design. The first thing I want to do is select the members that I'm interested to design. So under my views tab, let me view here just the members by type. And we're going to select everything except for those rigid elements. We'll go ahead and hide those. So for example purposes, I'm only going to design these 5 members here, just a short list on the right-hand side. Now my sets of members, if you remember way back when, we generated those sets of members because we have the ability to design them in this add-on module as one continuous member. So once I've defined my members for design, I'm going to choose my LRFD load combinations for consideration of my ultimate limit state design. And we also have the ability here to check deflection. So I can choose my ASD load combinations and move those over to the right-hand side. And it's really just as easy as moving down this list here. So under materials, the aluminum 6061 was brought in from RFEM, no changes there. Our cross section, same concept. We have our custom extruded section, and we have our tube element, again, brought in from the main program. The intermediate lateral restraints, this is not applicable to our box type sections today, but this would be any top or bottom flange bracing in the lateral directions. Under effective lengths, this is essentially stability design. So only our members are listed here. And we have buckling about the strong axis, we have buckling about the weak axis, and then we have lateral torsional and flexural torsional buckling. Now each one of these has the relevant effective length factor K, as well as the effective length factor times the unbraced length. Everything defaults to the full member length here. Now for a typical tube type section, we're probably not so interested in lateral torsional buckling. It's not a concern, so we can maybe uncheck all of these options. For example purposes today, I'll just continue to show you just essentially what this looks like and how our input data will vary. So with lateral torsional buckling for our beam elements, notice that with the lateral torsional buckling strength M-sub-E, we have the ability here to design it either according to chapter F or an eigenvalue analysis. An eigenvalue analysis will actually take this member, remove it from the structure, and run a separate eigenvalue analysis to determine the critical buckling moment. So a little bit more of a theoretical approach. Now, realistically, we should get approximately the same values, whether we choose to design according to chapter F or the eigenvalue, just again, a little bit more of a theoretical approach. We also have the effective lengths for the sets of members. Same concept here, but this only applies to this long set of members. Buckling about the strong axis, buckling about the weak axis, and again, lateral torsional, flexural torsional buckling. Now, I'm going to actually jump down to this next table because this does affect the current table that we're looking at, and this is called nodal supports. So once again, what we're going to do with this set of members here is we're going to extract it from the rest of the model to run a separate analysis underneath the hood for only this set of members. And if I create an isolated view here, what this table has me do is to input in the individual supports for this eigenvalue analysis. So up at the top, we have a support where we've restrained it in the lateral direction. We've also restrained the rotation about the X prime axis, which the axes are shown up here at the top. Down at the bottom, we have an additional support. And for this, what I'm going to do is to restrain it in the lateral direction, but also rotation about the Z prime axis. So rotation about its own axes here, and I'll uncheck rotation about the X prime. But remember, we also have these truss elements framing into each one of these nodes. So what we want to do here is to select each one of these graphically, and I can select them here back in the main program RFEM. And finally, our last node here. And for these, all I'm going to select here is a lateral restraint. So now we can see each one of those individual nodes set here for that set of members. If we jump back to the effective lengths, notice a lot of this information is now grayed out because the program's going to refer back to the nodal support table here in order to calculate the lateral torsional, flexural torsional, weak axis, unbraced lengths, effective length factors, and everything related to that with that eigenvalue analysis. Now, strong axis buckling is not addressed by this. So if we kind of pull this down, we see here we actually have this column framing up here, which is going to give us a little bit more capacity than the full member length here. So this is a little bit longer than 10 feet. So what I'll do is just to manually override my unbraced length here for my strong axis direction to about 27.20 feet. Moving on to member hinges, if we had any member hinges along this set of members, we could define that here. Serviceability data will allow me to check my deflections. So what I can do here is to choose my member, and I will select my members graphically. So we can design the same members or even different members for serviceability within the same case. And we also can check our sets of members if we're interested in checking deflection for the sets of members. I click OK. Notice everything defaults to the full member length, which will be related to the limiting deflection ratio. We can set a pre-camber. We also set if it's a beam or cantilever. I'll show you in just a minute where we can set that limiting deflection ratio for those serviceability checks. Before we do, I just want to visit this last table here, which is parameters for members. For this, this will refer to the tensile strength according to chapter D for our members. And in particular, section D32B states that if tension is transmitted by fasteners or welds through some but not all of the cross-sectional elements of the member, well, then we should use the effective net area. And the effective net area equation is actually given in this section in this standard, and it depends on A sub n, which is the net area of the member shown here, as well as the eccentricities of the connection. And ultimately, we use these variables to calculate the effective net cross-sectional area, which is used for the tensile rupture according to section D2B. So we don't have that scenario here, but I just wanted to quickly explain what that was all about. Finally, before we run our calculation, just to visit the detail settings here. So remember I said that this is where you would find that bridge versus building structure if you were designing according to ASD 2015 or 2010. You do have the ability to change the local buckling method here according to chapter F. By default, this is set to the weighted average method, but we have the direct strength method and limiting element method also available to us. Under the serviceability tab, this is where we can set our limiting deflection ratio. And currently this is set at L over 360, but for this tent structure, let's say we're not entirely interested in larger deflections, we don't have any finishes, this isn't really a building susceptible to human perception of large deflections either, so we can decrease this to maybe L over 180. So now that I have all of my input data, we're finally ready to run our calculation. And once again, for the sake of time, as we near the end of the webinar, I have already saved these results within the aluminum ADM module. So I'm going to pull up the module, and what we see after we run the calculation is our table results here, where we can view the design by member. And you'll notice as I scroll down through this member, again, everything is synced up. What else is powerful is showing this red arrow here for the relevant check. And each one of these members is going to have all checks from the standard shown to us. So for example, if we're looking at member number 559, we have the cross-section checks for compression according to chapter E, bending about the y-axis, biaxial bending, and so on. All of the relevant variables are shown to us here, as well as the references. Now, if you remember way back when, we have this custom extruded section, and I was talking about the local buckling abilities. Well, if we expand this tree here, sure enough, here are all of our elements that are classified for local buckling according to chapter B. So again, incredibly powerful here in order to check the local buckling of these custom sections. We also can view the design by sets of members. So same concept here. We're viewing just all the information. Remember, for each one of these members and sets of members, we also did that eigenvalue analysis. So we have the ability here to view the mode shape. So if we scroll around to view the mode shape of this particular set of members, this would be related to the lateral torsional buckling analysis. The program pulls out that member from the rest of the structure. So pretty powerful in what we can do there as well. Now, we can also take all of these members. I know it's a little bit overwhelming, so if we're just really interested in the max design ratio for each member, we can use our filter options here. And we'll see that serviceability is controlling for many of these, while stability analysis is controlling for several others. And ultimately, we're getting our max design ratio here of 0.35, which we have our green smiley face because we are well below 1.0 here. Remember, all this information you can export to Microsoft Excel just at the click of a button for further sorting. That includes here a material takeoff list if we wanted to export that to Microsoft Excel as well. Now, all of this information is shown graphically here. So just to lastly touch on this, we're within the RF-ALUMINUM ADM module. We're just viewing our results graphically here back in RFEM. So you'll notice that we can turn on our ultimate limit state here just to view for each one of these members what that design ratio is. Perhaps we want to turn on the serviceability. We can see serviceability is fairly low until we get to this member down here at the bottom. So again, if we're just interested in viewing this information graphically rather than that table format, it might be interesting for us to view it here back in RFEM. So hopefully that was a quick overview of aluminum member design. This model will be available on our website where you registered for this GoToWebinar, so you can download it and kind of just see all of the different settings that I have set. So what we'll do now is go ahead and jump back to the PowerPoint here to conclude our webinar today. As always, I know this is quite a bit of information, but certainly feel free to visit our website at delubal.com to learn more about RFEM, these add-on modules, RWIND Simulation. And again, we have all of these previously recorded webinars that will go into a little bit more detail on any one of these topics on our YouTube channel. I also want to let everyone know that we do have an online training tomorrow at noon Eastern time. It's 4 hours, it's $250, and it's worth 4 PDH as well. So if you're interested in more of the basics of RFEM, such as drawing members, the interface, how to run an analysis, I would certainly encourage you to sign up for that. If you're interested in that, go ahead and shoot us an email at info-us@delubal.com. You can also see our phone number available here to our Philadelphia office. So again, online training tomorrow, or anything else that you have questions about today's presentation or our products, feel free to contact us here, phone number or email at our Philadelphia office. So we will have many more upcoming webinars. You can always register on our website at delubal.com under support and learning webinars. As most of you know, I tend to send out an email about a week before these take place, so keep an eye out for that. PDH certificates will be emailed automatically to all participants today who were here for the full presentation. So it is required from the various states that we are pre-approved providers that the attendees be here for the full 60 minutes. So anyone who qualifies for this, you'll automatically be getting your PDH certificate usually within the next day. So it's not automatic right after the presentation, but usually within the next 24 hours. If you watched with a colleague or under a colleague's registration and you do need PDH, please send that request at info-us@deluwal.com. So again, if you yourself did not register for today's presentation with your own name and your own email address, but you were here for the full 60 minutes, please request that PDH to info-us@deluwal.com. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at our next webinar. Thank you.